So we do want to get to end behavior. That's our ultimate goal here. But before we can talk about end behavior, we've got to think about, what's happening at the ends of the graph, and we have to write our slant asymptote. So you'll notice that we have you doing these characteristics, writing out these characteristics in a set order every time, and there's a reason for that. Because by finding them in that order, it makes it a little bit easier to write your domain and your end behavior. So for end behavior, it's very much connected to, I don't like that color. End behavior is connected to either your horizontal asymptote or your slant asymptote, depending on which one you have. So that's why we say early on in the process, figure out what that horizontal or slant asymptote is, because it'll help you write that end behavior. All right, so knowing that, let's go ahead and figure out what the slant asymptote is for this graph. So our slant asymptote is this right here. And I need to be able to write the equation for that line. And I know it's a slant asymptote and not a horizontal asymptote because it's not horizontal. Okay, and you can either have a slant or a horizontal. You can't have both. I realize I'm not going to write this in the correct blank. Please do not get hung up on that. I'm just using the space I have available. So to find the slant asymptote, I'm going to think about how I write the equation of a line, which is y equals mx plus b. Okay, that's the easiest way to write the equation of a line when I can see the graph. So the two things I need to know to be able to write that equation are the slope and the y-intercept. So I start out by looking for my y-intercept. My y-intercept for the slant asymptote, okay? We're not talking about necessarily the y-intercept for the function. We're just focused on writing the equation of the slant asymptote right now. The y-intercept for that slant asymptote, it goes through the point 0, 0. So my y-intercept is 0. My slope, so this is when you have to sort of count rise over run. If you think back to geometry and even algebra 1, you talked about slope triangles of a line. It's kind of that same thing. So I'm going to look for another point as what we call a lattice point. It's just a point where it's easy to tell what the coordinates are. And it looks like you could use any of these points that I'm going to kind of put on here. So any one of those points would work. Now, the question becomes, how do you count that slope, right? So I'm going to go up to here because right here is 1. I'm going to go up here and then right, however many I'm going to go right. So I go up 1, right 4, and there's my slope triangle. So my slope, and it's positive because we're moving up when we look at the graph from left to right. So my slope is 1/4. So the equation of the slant asymptote is y equals 1/4 x plus 0. You can write the plus 0 if you want. You don't have to. Now, like I said, the end behavior is very closely related to the slant asymptote. And here's why. Let me get rid of this here. If I look at the ends of my graph now, okay, so this part of my graph and this part of my graph. Okay, I'm just focused on what's happening at the extremes. I don't really care about anything that's happening in the middle of this graph. It does not matter. It's irrelevant. The only thing that matters is what's happening at the ends of the graph. So when I look at the ends of the graph, I'm going to figure out what are the ends of the graph approaching as far as a y value goes. So when we write end behavior, it's always written this way. So it's always written as x approaches negative infinity, y approaches, and then we fill in the blank. And then we also do as x approaches positive infinity, y approaches, and once again we fill in the blank. Everything that I've written here doesn't ever change. Okay, that's always the same. The only thing that's going to change is what we write inside the box there. So that's when I go back to my graph and I try and figure out what's happening. So when we look at as x approaches negative infinity, what that's saying is as the x's get really, 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 really small, or as we approach negative infinity. So if I continue to move away from the center, away from 0, 0, out towards negative infinity on my x-axis, my x values are continuing to decrease. What's happening to my y value? What is my y value approaching? And you have two choices here, right? You could either say, some of you might say it's negative infinity. You're not wrong. A little more precise way to represent that end behavior would say, well, we know it's approaching and it's staying really close to that slant asymptote. So it's just approaching 1/4 x. That's what we would write in there for our end behavior. And then we could do the same thing on the right-hand side of the graph. So as x approaches positive infinity, we're just saying, look at the right part of your function. As you continue to move out towards positive infinity on the x-axis, what's actually happening with your y values? And if you look at your y values, they're staying really close to whatever the y value is for this line. And that's your slant asymptote. So we would write the same thing here. It's just 1/4 x. We're looking at the big picture here. Now, if you wrote positive infinity there, that's not wrong. But we can be a little more precise with that 1/4 x. And remember, the key to a slant asymptote is, or any asymptote, is that your graph wants to stay close to that asymptote, okay? It has sort of like a magnetic property for your function. So as you move further away from the middle of your graph, as you move further away from 0, 0, that function continues to stick close to the slant or horizontal asymptote. And that's why it affects your end behavior the way it does. So questions on end behavior. There were a lot of questions there. Does that help? And just type yes or no in the chat for me. And if not, elaborate a little bit for me so I know if we need to talk a little bit more about it. All right, I'm seeing lots of yeses. That's good. Okay, so then let's talk about domain for graphs that have a hole in them, because that was another question you guys had. And we'll just we'll slide down here to problem number 5, because there is a hole in that graph. So just like end behavior is directly connected to your slant or your horizontal asymptotes, when you think about your domain, so domain is directly connected to two things: any vertical asymptotes, or, well, I guess I should say, and any holes in the graph. So once again, if you know those two things, if you know what your vertical asymptotes are and you know what the holes in the graph are, you should be able to write your domain without even seeing the graph, really. So let's find those things on our graph. When I look at where my vertical asymptotes are, I see one here, I see one here, and I see one here. There's 3 vertical asymptotes this time. So vertical asymptotes, let me write those down here. And remember, our vertical asymptotes represent the equation of a vertical line. So it's important that we write them as an equation. So I would write x equals -3, x equals 0, and x equals 3. The second thing that's going to affect my domain is any holes in the graph. So there is one hole in the graph, okay, and I kind of highlighted it there over here at the point 4, 0. So I'm going to write that down. Any holes in the graph are important to note at 4, 0. Now, the domain is very closely related to all of those x values. And all we're doing when we write the domain is we're telling the person looking at our work where any breaks in the graph might be, where any asymptotes or holes might be in the graph. They're called discontinuities. So we're looking for those discontinuities and we're putting that within our domain. So when I try to show that on my graph, here's how I try to maybe initially try to write the domain. So I'm going to show you guys how I would suggest that you try to write the domain. So you start at the left side of your graph. And here's what I know. I know that this is going to keep going forever off towards negative infinity for x. So I know I'm coming from negative infinity, and I'm able to keep tracing because there's no breaks. I'm able to keep tracing with my pencil until I encounter the x value -3. And then at that point, I'm going to have to pick up my pencil and go over that x value. I can't trace through it because it doesn't exist. I have to pick up my pencil and skip over it. That tells me what my first part of my domain would be. So that first part of my domain is everything from negative infinity to -3 is good. But when I get to -3, that's when I encounter a problem. So we use that union symbol. It's like and. So the union symbol in mathematics just means and. It's just a group of things that go together. So that's all that represents. So now I've got that first part of my domain. And if I continue to kind of pick up where I left off, so right here, I then have to pick up my pencil, and then I start on the right side of -3. And everything from there until I encounter the x value of 0 is fine. So then my next part of my domain is saying that everything between -3 and 0 is good. Now I want to point something out before we finish this. You'll notice that I'm using parentheses here, okay, and not brackets. And if you remember with domain, brackets means that you can include that value in your domain. That means that there is a point that has that x value. Here's what I know about this graph. There's no point that can have an x value of -3. So that's why I put the parenthesis on either side of -3. Because what I'm saying is that I can include every point up to but not including -3 on either side. And then I can continue tracing. So now I've encountered another discontinuity. I've encountered this x equals 0. I have to pick up my pencil again, and I can start now starting a new trace on the other side of x equals 0. So that tells me I've got another section to my domain. So I continue tracing, and I can see that from 0 for the x-axis until I encounter 3 on the x-axis, I'm good. I can trace any value between there. I don't have to pick up my pencil. So then my next set of my domain is going to be from 0 to 3. Now, I realize that when I hit +3, I'm going to have to pick up my pencil again. So now I trace on the other side of +3, and from 3, I'm good until I get to 4, because there's a hole in the graph right there. So then I have to pick up my pencil again. So now I have everything from 3 to 4, not including 4, and I have to pick up my pencil to go through 4 because there's a hole in the graph right there. I can't keep tracing right through it because that point doesn't exist. I have to pick up my pencil and I have to hop over that point, and now I can keep going forever and ever and ever and ever and ever. So now I know that everything from 4 to positive infinity is good. So my domain ends up being this set. It's all 5 parts of what I've written here that defines the domain for that graph. And it's directly related to your vertical asymptotes and your holes in your graph. So you'll notice, I'm going to highlight these so you can kind of see what I'm saying here. You'll see that those x values that I wrote up above show up in my domain. In fact, you don't even really need the graph if you wanted to write your domain. Okay, so you'll notice that each of those x values represents a break in the graph. And then you can create your domain from there. Are there any other questions on domain?